You have now seen the basic planning graph, the nodes and the edges that make up this graph, and you have seen how it can be understood as a reachability analysis. The planning graph is a layered graph consisting of proposition and action layers. When we search for a plan in this graph, what we will get as a result is a layered plan, and we will look at those next in a little more detail. In layered plans, we will have multiple actions that come from the same action layer, which means we will effectively try to execute these actions in parallel. Now, we've already seen that this may cause problems, but this will not be the case if all these actions are independent. And here's an example of what independence of actions means. Looking at the two actions in this action layer A2 here, we have the action of moving the robot R from location 1 to location 2, and we also have the action of loading container A onto the robot R at location 1. And what we see here is that MR12 has a negative effect R1, so it deletes the fact that the robot is at location 1. But if we look at the other action, LAR1, that has a precondition R1. So what this means is one action deletes a precondition of the other action, which means these two actions cannot be executed in parallel. These two actions are dependent. Similarly, if we look at this action again, and now as another action MR21, so one is moving the robot from location 1 to 2, and the other one is moving the same robot from 2 to 1. What we see here is that the first action, MR12, has a positive effect R1, whereas for the second action, this is actually a negative effect. So one action is trying to assert the fact R1, that the robot is in location 1, and the other is trying to delete the same fact. Again, this means these two actions cannot occur together. They are dependent actions. But to show you that not all actions in this action layer are dependent, let us look at MR12 and MQ21, for example. These two actions are independent. Their effects and preconditions don't interfere with each other, so we can execute those two actions together and in parallel. And here is a general definition for what it means for two actions to be independent. We can say that two actions A1 and A2 are independent if the following conditions hold. And what these conditions express is very simple. They say that the effects and preconditions of those actions must not interfere. And that's exactly defined the way we've seen it just in the example. So we've seen that the negative effects of one action may interfere with the preconditions of the other. So we have the negative effects of A1 intersected with the preconditions of the other, and that must be the empty set. And the same goes for the positive effects. So we have the negative effects intersected with the positive effects. That again must be the empty set. Or in other words, the negative effects of the first action must not be a precondition or a positive effect of the other action. And the first condition states this for the negative effects of A1, and the second one is simply the symmetric case for the negative effects of A2, which must not be preconditions of A1 or positive effects of A1. That's what it means for two actions to be independent. And we can easily generalize this definition to a set of actions pi. We can say that a set of actions pi is independent if every pair of actions in this set is independent. So we must not have a single pair of actions that are dependent in this set. Then the whole set consists of independent actions. And one important thing here you can see in this definition is that the independence of actions does not depend on the planning problem, which means this can be computed before we start our planner, before we search for a solution to our problem. And also, you can see quite easily that the independence relation that holds between actions is symmetric, because in the definition we have seen that these two cases for A1 and A2 are symmetric. And here is the definition we've just seen expressed as an algorithm in pseudocode. We define a function independent that takes two actions and returns true if and only if these two actions are independent. And what this function does is simply go through all the negative effects of the first action and test whether they're also either a precondition or a positive effect of the second action. If this is the case, then we can return false, because we know these two actions are not independent. They are dependent in this case. And then we also need to do the same for the symmetric case. So we go through all the negative effects of the second action and test whether they are a precondition of the first action or a positive effect of the first action. Again, if this is the case, we can return false. The two actions are dependent. If this is not the case, so if we go through both these loops and don't return false, then we must have a case where the two actions are independent and we can return true. In terms of time complexity, you can easily see that this algorithm has polynomial time complexity. In fact, it's linear in the number of preconditions and effects that an action might have. So if the number of preconditions and effects an action might have is b, this algorithm runs in O of b. This assumes that these element tests here in the algorithm can be done in constant time. And I've already told you, since action independence is independent from a given planning problem, this can be all pre-computed. And I'll leave it up to you to work out how much storage this will actually take in computer memory. Now that we've seen what it means for a set of actions to be independent, we can talk about the application of a set of independent actions in a given state. And this is quite straightforward. So we can say that a set of independent actions is applicable in a state S if the following holds, namely, the union of all the preconditions over all the actions must be propositions in our state S. It should be obvious that if each of the actions has its preconditions satisfied in the state S, then this individual action will be applicable. And if this is true for all the actions, preconditions, then all the actions are applicable. And then the result of applying a set of independent actions, so this is our set pi here, independent actions, is defined as follows. We extend the definition of our state transition function gamma to now take a state S and a set of independent actions pi. And the result will simply be all the propositions that are true in S minus the negative effects of the set pi plus the positive effects of the set pi. And when we talk about the preconditions, if positive effects or negative effects of a set of independent actions pi, we simply mean the union over all the actions in that set pi, preconditions, positive effects, or negative effects. So this defines applicability and state transitions for sets of independent actions. Going back to what I said earlier, what we will be looking for is sets of independent actions in action layers in our planning graph. And when we want to turn this into a sequential plan, we need to be sure that we can do that. And this is what this proposition gives us. If we are given a set pi of independent actions that are applicable in a state S, then we can take any permutation of those actions, A1 through AK, so those are the actions in pi, and this is a permutation, any sequential order of those actions, and the following will be true. This sequence of actions, A1 through AK, will be applicable in our state S, and the state that we get to when we apply our set of independent actions, this is the extended definition of the state transition function that we've just introduced in the previous slide, will be the same state as the one we get when we take the state S and apply the sequence of actions A1 through AK. And remember, this does not depend on which sequence we've chosen. So we can take any permutation and the resulting state will always be the same as when we apply the set of independent actions. That simply means we can forget about the execution order of independent actions because we can take any order we like. Now we can define what we mean by a layered plan, which is the type of plan we'll be looking for in our planning graph. So suppose we are given a planning problem consisting of a set of actions, an initial state, and a goal. The set of actions here is a set of propositional actions, and we're dealing with a propositional planning problem. Then we have a planning graph consisting of nodes and edges, where the nodes are given by the first proposition layer, the first action layer, and so on, always alternating action and proposition layers, as we've seen it earlier. Then we can define what we mean by a layered plan over this graph, and we define it as a sequence of sets of actions denoted here by this big symbol pi. And this is the sequence of actions, pi 1 through pi k. And for each of these sets, we must have the following conditions true. So the ith set in this sequence, pi I, must be a subset of the actions in the ith action layer of the planning graph. So that would be for A1, this would be this one here, for A2, this one here, and so on. So pi I must be a subset of the actions in that action layer, which are of course a subset of all the actions that are available. Then this set pi I must also be applicable in the state represented by pi minus 1. That is the proposition layer preceding the action layer we're just looking at. Note that this is not necessarily a consistent state. And then, of course, we want all our actions in pi I to be independent. So the main thing here is that our layered plan is a sequence of sets of independent actions, where each of these sets must be from the corresponding action layer. Now that we know what a layered plan is, it's fairly straightforward to define what it means for a layered plan to be a solution to a given planning problem. So we have a layered plan consisting of sets pi 1 through pi k of independent actions chosen from our planning graph. And we have a planning problem given by the set of actions A, initial state, and goal. Then this sequence of sets of actions is a solution for this planning problem if the following conditions hold. Firstly, our first set, pi 1, must be applicable in our initial state. Then, for every subsequent set, pi j, so j must be greater than 1, this must be applicable in the state that we get from first applying pi 1 in the initial state, then applying pi 2 in the state that results from this, and then applying the next set of actions, and so on, up to pi j minus 1, applied in the state that we get when we apply these other sets before that. And in this state, pi j must be applicable. And the third and final condition is simply, if we look at the state that we get from applying all those sets of actions in sequence, so starting from pi 1, then pi 2, and so on until we get to the last set, pi k, we get a state, and in this state all the goal propositions must be in this state. So that is what a layered solution plan is, and that's the kind of plan we'll be looking for in our planning graph.